were mentioning in the video, a lot of people don't really understand like what exponential growth is, or what it means for something to increase in an exponential way. And that's actually referred to as exponential growth bias. And people speculate, like there were articles that like people speculated, for example, during the pandemic, that people were less likely to use what the precautions like masking and social distancing that were suggested in order to try and flatten the curve, like change the growth from being exponential to more of like a logarithmic model, if they didn't actually understand what it meant for something to increase exponentially. I had an article, maybe I'll try and share it with you guys when we come back, about that. But a lot of people tend to use, like, throw around like, oh, this is increasing exponentially, when it's not. Like maybe it's increasing in a linear way or some other sort of model. So we're really, like, one of our goals is for you guys to understand what it actually means for something to be increasing or decreasing exponentially, okay, or following an exponential model. So thinking about this scenario, Miss Dorset's son Cameron, he's 5, got $100 for his birthday, and he has decided to deposit this money into a savings account instead of storing in his dresser drawer. This is a very smart decision on Cameron's part, but why? What's the difference between storing his money in his dresser versus a savings account at a bank? So if he puts his $100 in his dresser drawer and goes back a year later, how much money is going to be in his dresser drawer? $100 still, as long as he hasn't like touched it. Like if he's just left it, there's $100 a year later. The difference between him storing the money in his dresser drawer versus like putting his money into a savings account is that a year later, will there still be $100 in the savings account? No, what would have happened? It would have increased exponentially, because what do banks give you as incentive for putting your money in the bank so that they can do other stuff with it? What do banks do? What do banks give you? Interest. They pay you interest so that you put your money into a bank. Now it's like a savings account is normally some like crazy small percentage that they'll pay you. But they'll pay you some interest, and normally they'll give you like the information as like an annual interest rate, which would mean like the amount of interest that's applied each year, but really then there's like an even smaller percentage that would be applied like maybe like each month, like whenever you get your bank statements. But as incentive, the bank will pay you interest. So this is not realistic, but like let's say that Cam puts his money into a savings account that pays 5% interest annually. And annually refers to once a year. Again, not realistic. Oh, you guys, you know what I forgot to do? Oh, Leela, Addison.
I'm not on it. I think it's open in the background.
Okay.
I can close it though.
Yeah, can we close it? Okay. So let's say they puts it into a savings account that pays 5% interest annually. So like he puts whenever no time has passed. So like when he first puts the money in, so after 0 years, he would have $100, that's the initial amount, $100 in his account. Then, if nothing else, like he hasn't done anything else to the account, like hasn't put any extra money in, after 1 year, how much money would he have in the account? $105. $105. So you're taking the amount that's in there, finding what 5% of 100 would be, so 100 times 0.05, and then adding it onto the original amount. So after 2 years, actually, can we get calculators out because we're going to want to use them here today? So that means after 2 years, if I take 105, multiply by 0.05, and then add that, so 525, and add that to 105. So after 2 years, there would be $110.25. And then after t equals to 3 years, so taking that previous amount, multiplying by 0.05, and then adding to 110.25. So then we would have he would have $115.76. Okay, so that's without him having to do anything. His initial deposit would be increasing exponentially because it's increasing by a common ratio, a common percentage each period. Where the length of the period in this case is based on, that's 5% interest annually. So the length of the period is 1 year. So by the end of each period, the previous amount has increased, not by like the same amount each time, but it's increased by a common percentage. So you could imagine, like, at first, like, the growth is slow, but like you could imagine, like, after 20 years, like if you're taking 5% of a large amount, then you're adding larger and larger amounts onto the previous period's amount, okay? So this is how numbers, whenever exponential growth is present, like how values can increase really quickly. So the intuitive definition of exponential growth or decay, and this is not in your textbook, but my intuitive definition of exponential growth or decay is when a quantity or an initial amount increases or decreases exponentially. So a quantity that increases or decreases exponentially will grow or decay by a common percentage per period. And they referred to common percentage as like a common ratio, same thing. Right? Interpreting like 5% as being a decimal, 0.05, like that can be thought of as the common ratio. So if we think about it, especially like juniors, or actually those sophomores in chemistry too, you guys have probably talked a little bit about exponential growth and decay. I had mentioned like COVID-19, like number of cases was an example of exponential growth. Can we think of, besides money, we also talked about money, like in a savings account or some sort of savings account or an investment account, was an example of exponential growth. Can we think about any examples that you've maybe talked about in your other classes of exponential decay? In chem or bio, have you guys talked about like, oh, go ahead.
Half-lives.
Half-lives, yeah, so half-life, but what would the application, like what can be modeled with half-lives?
How fast it takes for a substance to decay upon being exposed to radiation.
Okay, so oftentimes, like whenever doctors are prescribing medication to somebody. You know how like they always want to know like what your weight is and stuff. They have to take that into account to figure out what your appropriate dosage is. And the dosage is based on them knowing what the half-life of the medication is at a specific amount. Like how long it would take in order for the substance to decrease by 50%. So medications are an example, like medication in your system can be an example of decay. Or like if we know the half-life of like caffeine in a cup of coffee, like you could figure out like how long it would take for like you drink a cup of coffee or like a Diet Coke, like how long before the amount of caffeine in your system is at 50%, and kind of track, or like, well, what if I drank another cup of coffee like 15 minutes after I drank my first cup of coffee? Like how long is the caffeine going to be impacting me? Or at what levels in your system is the caffeine going to be impacting you? And some of that is very individual and like based on an individual person, but some of it like has been studied and they can determine like how much would actually be in your system based on the half-life of the caffeine. Any other ideas? And either bio or chem, have you guys talked about carbon-14 dating? Which class?
I think it would have been 10, but I've definitely heard of it, but I'm not sure if it was.
I think it was later in the year.
Yeah.
Do you guys remember what carbon-14 dating is?
Somehow when you're able to like grab a nail and like able to like check how much carbon there is so you can see how old it is.
That's exactly it. Because we know what the half-life of carbon-14 is, if you know how much carbon-14 is like left in bones or fossils, like you could determine how old, like how long something has been around. So carbon-14 dating is an example of exponential decay. Okay, so the textbook definition of an exponential growth or decay model. So coming up with like a mathematical model, an equation, an exponential equation that can model exponential growth or decay. An exponential function is of the form y equals 2a times b to the x power. Notice where the x is. The x is in the exponent position. Now there's some restrictions on the different parts, the different quantities that are in this equation. Like a can't be equal to 0, b, the base has to be greater than 1, or between 0 and 1. B is referred to as the base. And b has to be a real number with the restrictions stated above. And we're going to explore, well, why do we have to have these restrictions? So we're going to next talk about, like, why are these restrictions on the base? Like, why does the base have to be greater than 1? And why does the base have to be between 0 and 1? A is the vertical stretch or shrink factor, like thinking about from a transformations perspective. It's also the initial value, because if you were to let x equal to 0, b to the 0th power would always be equal to 1, meaning that the output would be the initial value, or it would be the y-intercept of the graph. So let's check out the why we have these restrictions on the base as well as the vertical stretch or shrink factor, or that initial value of the function. And we want to understand these restrictions to these values because next semester when we start talking about logarithmic functions, we're thinking back to these restrictions to understand why we have certain restrictions on values in logarithmic functions. Okay, so understanding these is important. Like, what if b was equal to 1? I'm going to do these different cases. So if b was equal to 1, well, then we would have y equals to a times 1 to the x power. Well, if we were to substitute any real number in for x, 1 raised to the 7th power is 1. 1 raised to the negative 1,000th power would be 1. So this would actually just simplify to be y equals to a, which what does the graph of y equals to a look like? Y equals to a number. It's just a horizontal line. Meaning as x is getting larger, the y values would be staying the same. There's no exponential growth or decay occurring. Now if b was less than 0, so for example, if we had y equals, let's say that a is 1, and let's make b equal to like negative 2. If we thought about making a table of values, so like if we let x equal to 1, y would be negative 2. If we let x equal to 2, y would be negative 2 squared would be what? 4. Okay. Negative 2 cubed would be negative 8. And then to the 4th would be positive 16. So do we see what's happening with the y values? What's going on? What are we observing with the y values whenever the base is negative here? Well, we have negative 2, then we have positive 4, then we have negative 8, and then we have positive 16. So the values are increasing in magnitude, but they're kind of bouncing back and forth between positive and negative. So if you were to think about graphing those points, would you end up seeing like exponential growth or decay happening? No. The graph would be kind of freaking out, going back and forth between positive and negative. We actually describe this sort of behavior of a graph as the y values are oscillating. They're bouncing back and forth. They are oscillating because they are switching back and forth between positive and negative. So negative base, no exponential growth or decay. The graph is just kind of freaking out. Like, let's even look at like it doesn't. It doesn't even know what to do. It doesn't graph anything. Okay, and then the last one, if a was equal to 0. Well, if we have 0 times b to the x power, any real number times 0 will just be 0. So we again end up having a horizontal line. Which would not exhibit exponential growth or decay. Okay, so B cannot be 1 and B cannot be negative. And then A, the vertical stretch or shrink can't be 0. Okay, so all exponential equations have these restrictions. Questions, you guys? So what I want you guys to do next, take a moment, go ahead and fill in these tables. So what I mean by that is, like for y equals 2 to the x, well then you're thinking about y equals 2 to the negative second power. Thinking about exponent rules, I'm kind of assuming that you're remembering exponent rules. If you have a negative exponent, what does that mean? Yeah, it means you can move that to the denominator. That's the same as 1 over 2 squared, which would be 1/4. So negative 2 comma 1/4 would be a point on the graph, and you could come down here and you could graph that. So go ahead and fill in your table for both of these functions. So y equals 2 to the x and y equals 2 to the negative x. And then we're going to look at what the difference is between the graphs, because the equations look pretty similar. Yeah?
Can you go back up for a second?
Mm-hmm. So yes, finally you would be using distance equals rate times time. Or at least because you know that the Turkey is 0.7 miles. And do you understand the situation? Like, we're leaving the parking lot, I go one way, he goes the other way. So thinking about like when we would meet, we've traveled how many miles? Like together, we've traveled. Yeah, like my distance plus his distance would be equal to 0.7. How's it going, you guys? All right, you guys, do our graphs agree with each other? Are we still working on them? Elliot, you still have like over 18 minutes, by the way. Interesting. We're going to do it together. Have you guys looked at the rosters for your roster for next semester? Yeah, but like Addison and Kellyanne, you guys are with Ryan, Ion, Elliot, Ellis, David, and Regan. And then Cans with everyone else for this one. Did not really balance the classes very well. Okay, well you're saying speed in miles per hour, but then for their rates, like the speed for amount of time, you're using you're mixing your units.
What's your H?
So I have to do for next semester?
Yeah.
I have
I'm in that as well.
I have, wait, who do I have? It's in my seminar.
It's gonna get good for
I have molecular, so let's
Maybe use the fraction.
because you listen to the same stuff.
Ryan's.
All right, you guys, do we have our graphs? What's the difference between y equals 2 to the x and y equals 2 to the negative x? Like from a transformations perspective, what has happened going from y equals 2 to the x to y equals 2 to the negative x?
It's a reflection of
It's a reflection across the y-axis, right? So thinking about it, that makes sense with these equations, right? This multiplying x by -1, that's a horizontal reflection, a reflection across the y-axis. Now the other thing is that we can think about rewriting y equals, I'm going to come down here to do that. We can also think about rewriting y equals 2 to the negative x as 1/2 to the x power, like that, where the base is thought of as being 1/2. Do we see that for exponent rules? I can write an extra step, actually. Thinking exponent rules, if we had 2 to the negative first raised to the x power, like rewriting the negative x, right? When you raise a power to a power, you multiply the exponents. And then 2 to the negative first power is 1/2. So we could think about the base in y equals 2 to the negative x as being 1/2. So a value that's between 0 and 1. Just pointing that out. Okay, so let's get into answering these questions. So let's focus on y equals 2 to the x first. What would the domain of y equals 2 to the x be? So reading the graph from left to right, thinking x values. what would the domain of y equals 2 to the x be? Thinking about what you could plug in for x and get a real output. All real numbers. Negative infinity to positive infinity. Now numerically, let's think about what the range would be. So we don't really have like an analytical approach for determining what the range would be. We're looking at the graph. You could maybe kind of eyeball from the graph, but you also have to do kind of a numerical analysis here. Like thinking, and this goes into our end behavior. If we were plugging really small values like negative 100, negative 1000, like negative 100 plugged in for x, that would be 1 over 2 to the 100th power. Negative 1000 would be 1 over 2 to the 1000th power, where the denominator would be getting larger and larger and larger and larger, but the numerator would stay 1. So the values would end up trending down towards 0. But is there any real number that you could plug in for x, Ion? Is there any real number we could plug in for x and we would get 0 for y?
Yeah.
What number?
Wait, can you repeat that again? Sorry.
Is there any real number that we could plug in for x where we would get, like, think 2 to a number, 2 to a power, that would give us 0?
No.
No, there's not. Okay. So the range, it's going to trend as x gets really small. The y values are going to be trending towards 0, meaning we could say for end behavior, as x approaches negative infinity, y would be trending towards 0, but y is never going to actually be equal to 0. So for the range, we could say from 0, and then as x gets infinitely large, what's happening to the y values? Like if you're plugging in large numbers in for x, 100, 1,000, 10,000, 100,000, a million, 2 to the millionth power, 2 to the billionth power are going to be incredibly large numbers, right? Meaning y would be approaching positive infinity. And we can see that in the graph, right? Like it's trending upwards. Now, because this happens, because y seems to be trending towards 0, in terms of end behavior, we can use, or we can come up with an end behavior equation to describe the end behavior of y equals 2 to the x. Since as x is approaching negative infinity, y is trending towards 0, we could say that there's a horizontal asymptote at y equals to 0. And it's only in, unlike the other functions that we've studied, the rational functions that we studied, it's only in the one direction. And then for y equals 2 to the negative x, kind of going off of like our knowledge of transformation, just kind of putting everything we know together. The domain would also be all real numbers. Is that horizontal reflection going to change the range? No, it will change the end behavior a little bit. But the range will still be 0 to infinity. But we would say as x approaches negative infinity, the y values are actually trending towards positive infinity, since we're taking the opposite of those really small values. And as x approaches positive infinity, y is approaching 0. So also has the horizontal asymptote right? This leads us to the horizontal asymptote at y equals to 0. We can think about exponential functions as having like a parent function form. Like the parent function for exponential functions would look like this: y equals b to the x power. And remember how parent functions, remember how when we talked about like for algebraic functions, so when we had y equals to like a rule that was just in terms of x, and like the basic arithmetic operations, remember how we had some key points on the graphs of the parent functions that then whenever we were thinking about graphing from a transformations perspective, we thought about applying the transformations, the list of transformations to those points. You good?
Yeah. Thank you.
Wonderful. And now you can enjoy Hawaii where you only have to think about your final exam.
Perfect.
So great.
Thank you.
Can you go to the right?
So now the parent function, the points that are easy to think about, and if I go back to y equals 2 to the x, okay, would be whenever x is equal to -1, the y value is just the reciprocal of the base. Whenever x is 0, and then whenever x is equal to 1. So like -1, comma 1 over b, 0, 1, and 1b. Okay, these are the points that you would use for transformations. So then for these next two equations, from a transformation perspective, there's actually only translations occurring in particular. We would be thinking about the parent function for each of these equations as being y equals 3 to the x. Meaning the points that we would be using for our transformations would be -1, comma 1/3, 0, 1, 1, comma 3. For f of x equals 3 to the x plus 2, what is that plus 2 doing to the parent function? Left 2.
Also, when I plug in -1 like into the function, I get 3 and not 1.
3 to the negative first?
No, because if it's -1 plus 2.
No, I know, that's for the parent function.
Oh, sorry, my bad.
So the parent function is y equals 3 to the x, right? We're going to take these points and apply whatever transformations to figure out what those graphs look like. You technically can make a table of values, but thinking about shifting like the entire graph and from a transformations perspective, I think is a little more efficient and a little bit more useful for going forward. And then the plus 2 down here, so g of x equals 3 to the x plus 2. That plus 2 would be a what to the parent function? A vertical shift up 2. Vertical shift up 2. Okay, so if we thought about the parent function, the graph of the parent function would be -1, 1/3, 0, 1, 1, 3. You could think about plotting some other points, like 2, 9 would be a point. And thinking about what that graph looks like, the graph would have a horizontal asymptote at y equals to 0. Okay, but then to graph left 2, you're just thinking about shifting each of those points to the left 2. Easy peasy. Right, so that's for f of x equals 3 to the x plus 2. And then for the vertical shift up 2, thinking about all the points from the parent function shifting up 2. What else shifts up 2? The asymptote, the horizontal asymptote is also going to shift up 2. So thinking about the graphs of exponential functions from a transformations perspective is about as crazy as we get with the graphing. And we'll do the same with log functions. Like, it is not a graphing heavy chapter. So understanding those 3 key points for the parent function, like how to identify the parent function, and then everything else is just what you already know, transformations. Questions? You should have arrows on both sides to indicate the graph continues on. So why don't you guys try the next one? Identify what your parent function would be and the transformations occurring to the parent function, and then sketch h of x. If you're graphing by hand, you should label the asymptotes, just like you had to with rational functions. Okay, so you are identifying the parent function, list the transformations, and figure out what the graph of h of x looks like. And you check your answer with somebody else. I would also maybe think about, remember how for when we were studying transformations with algebraic functions, we thought about getting our equation into like the transformation form. So I would probably rewrite h of x. Oh, you can't see it. I would probably rewrite h of x like this, and so that I can read from left to right to identify transformations, having the vertical shift come last. All right, you guys, do we have our graph for h of x? This is what mine ends up looking like. I graphed the parent function as well. So horizontal asymptote at y equals to 1. The parent function is 2 to the x. There was a vertical reflection, a horizontal reflection, and up 1. So I took each of the points on the parent function, so like -1, 1/2, 0, 1, 2, 1, through that list of transformations. Vertical reflection, horizontal reflection, shift up 1, right? And then the horizontal asymptote, if you also think about taking that through the list, your vertical reflection goes nowhere. Horizontal reflection goes nowhere. But then the up 1 tells you what the vertical shift is. Or the vertical shift tells you where the horizontal asymptote lands.
Show you the steps, like at the top of the graph.
All right, let's talk about E, the natural base E. So like 2 and 10 and 1/2 are all common bases for exponential functions, like when we're talking about modeling. We'll get into this in January, but like 2 would represent like if something is doubling, like increasing 100%, a base of 1/2 would represent if something is decreasing by 50%. Okay. E, Euler's number, is also a common base, especially whenever it comes to like science applications. So E is an irrational number. Think of it like pi. Like you could never, like pi is the exact value of pi, like the exact representation of pi. Like you can come up with like a decimal approximation, like or start like listing an approximation. Like that's why there's like a contest on Pi Day for reciting digits of pi, right? Like you could never memorize all of the digits of pi, okay? E is the same way. It's an irrational number. It's known as the natural base, and it comes from evaluating the expression 1 + 1 over n to the nth power, which in January we'll reference this again. But thinking about evaluating that expression as n approaches infinity, okay? So as n approaches infinity, evaluating that expression, that value is trending towards what we call E. Now, it is a good idea to know, just like you guys, I'm sure know an approximation for pi, right? Like it drives me nuts that Mr. Kim lets ninth graders do calculations instead of using pi, using like 3.14 in their calculator. Drives me nuts, but whatever. Knowing an approximation of the value is a good idea. So 2.718, like knowing that that's an approximation of E is helpful. So then for graphing E, let's like think about y equals e to the x as being the parent function. And so let's use those values, like x equals to -1, 0, and 1, in order to figure out what the graph of y equals to e looks like. So like having e to the negative first, that's the same as having 1 over e. And 1 over e, if you put that into your calculator, do you guys have your calculators out? And you type in like 1 over e or e to the negative, like if you hit second ln, it pulls up e to a power to the negative first is approximately 0.368. e to the 0th power would be equal to 1. And then e to the 1st is that approximation, right? 2.718. So thinking about those points, 0.3, so maybe like right there, 0, 1, 2.718. And then same end behavior as the other bases that were greater than 1, so that we can think of there being a horizontal asymptote. At y equals to 0. And then if you wanted to graph y equals e to the, I'm going to skip this, but if you wanted to graph y equals e to the negative x, you could just think about there being a reflection.
Wait, sorry, can I just take a photo of it?
Okay, just for identifying like what would be an exponential function or not, like for an equation, because like being able to recognize like all of these, f of x, h of x, and g of x are all examples of exponential functions that maybe have different transformations occurring. So like f of x equals 7 to the x power, is that an exponential function or not an exponential function? Yeah, it's exponential. Base is greater than 1. It's good. What about x to the 7th? No, what type of function is that? It's a polynomial. Polynomial function. X to the x power. So since the base is a variable, no, this is actually known as an Aleph function, which I have never worked with, but it's called an Aleph function. Negative 2 times 15 to the x plus 1. Yep, exponential. There's lots of transformations. 4 pi to the x power. Exponential. 3 times 1 to the x power. Base can't be 1. It's actually a horizontal line, right? Like this would simplify to just be 3. Negative 3 to the x power. Yep. What about this? In parentheses, negative 3 to the x power. Remember how we talked about the base has to be greater than 0 or less than 1 or greater than 1? So actually no, and this is an example of, remember when we saw it would be oscillating if the base was negative? Oscillates.
What's the difference between G is G?
What is the difference?
Is it because it's a transformation? Or G?
What's the difference between those two equations? H has a parentheses around the base, right? So it's saying negative 3 is the base versus in G, it's only 3 being raised to the x power. That negative is indicating a vertical reflection, and that makes a difference. 0 to the x power? Nope. It's only equal to 0 for x greater than 0. like a horizontal line for x greater than 0. And then for j, that can actually be rewritten as 3 times 4 to the x power. Yes, this is exponential. Don't we only go till 27?
That's on Tuesdays.
It's not in our... Oh, we go to 38. Oh my God. I'm like looking at... I'm losing my mind. Okay. Losing my mind. Okay, so being able to look at an equation and identify, is it exponential? Is it not exponential? And then the last part, some of these are getting, like these ones I would consider to be bonus level. But we're going to look at coming up with the exponential function that could represent these graphs. So let's assume that this point here, I know it's not labeled, let's assume that that's 0, 1. Because it's saying, the question is saying, find the exponential function that's in this form, b to the x power. So ideas for how we could determine what the equation of this graph is. We need to figure out what the base is, yeah? So couldn't we, since we know a point, couldn't we think about plugging 2 in for x and 25 in for y? So then we're like, oh, b has to be plus or minus 5, but b can't be negative. So that means b is just equal to positive 5. So like y equals to 5 to, or it said f of x. So f of x equals 5 to the x power. And then same idea for the next one. Right, this is 0, 1. You can look at to 0, 1 to see, or for the point whenever x is equal to 0 to be like, is there a vertical stretch or shrink? But same idea. So we could think about plugging 1/8 in for y, 3 in for x. So what would b end up being equal to, you guys? 1/2. Notice that when the base is between 0 and 1, that ends up representing a graph that's decreasing versus whenever b is greater than 1, the graph is increasing. So f of x equals to 1/2 to the x power, which can also be written as 2 to the negative x, because if you thought about applying exponent rules, right, you would have this, which could also be written as this. Any of those forms would be appropriate. And then we're just going to step it up one notch where there might be a vertical stretch or shrink. Remember how a, whenever x is equal to 0, a represents the initial value of the function? Or the y-intercept? Well, in a and b, we're given the y-intercept. So, like, we know that when we're trying to come up with this equation, we know that we'll have y equals to 4 times b to the x power. And then we can just think about using this other point in order to figure out what b would be. So plugging in 22 for y, 5 for x, we can think about solving. So if we divide by 4, 22 divided by 4 would be 11 halves is equal to b to the 5th power. And then how would we finish solving for b? Yeah, so which I'm going to write as 11 halves raised to the 1/5 power. So then whenever we plug back into b, we would have 4 times 11 halves to the 1/5 power raised to the x power. And when we raise a power to a power, we have 4 times 11 halves to the x over 5th power, because when you raise a power to a power, you multiply the exponents. And then for b, we know that we would have y equals to 2 times b to the x, and then we could think about plugging that other point in. So 1/2 equals 2 times b cubed. If we divide by 2, we would have 1/4 equals b cubed. So b would equal to 1/4 to the 1/3 power. So y is equal to 2 times 1/4 to the 1/3 power, and then that's all raised to the x power. So we can think about writing that as 2 times 1/4 to the x over 3rd power, which since the numerator there is 1, you could also write that as 2 times 4 to the negative x over 3 power, like if you were using exponent rules. But either one would be appropriate. So either this, or this, or this. The others on here, which I think I'm going to leave, if you want to check them out for a challenge, you can. But notice that neither of the points that are given are the y-intercept, so it makes it a little bit tricky. You kind of have to think about setting up a system of equations and then solving for A as well as B. Okay, so you guys have homework due next class, 3.1 part 1 from the textbook. And then next class is review. I will have working on getting a document together that has like all of your quizzes, all of your tests, all of your reviews for each chapter in a document. So you'll be able to like use that, like blank versions of quizzes and tests to help you with prepping for your final exam. Yes.